Did we do the slide? Does it look familiar?
No, we didn't do it. Yeah.
Okay. I think these are neat because you're going to see, I think it's 4 different graphs, and actually we're going to go back and refer to this later. But since you guys don't have the color, the straight line is the acceptable limits. Okay. The blue line is the engine speed. So this is like emissions of a car. So how fast is it going? And did you ever wonder like how you, like if you're driving, how can I get to my best mileage? Like if I go 60, or if I go 50, or if I go 75. But anyway, this is talking about hydrocarbons that you are emitting grams per mile if you're going along this, how fast you're going. So let's see, where is the red line the smallest? How fast you can be going? I don't know. It's a hard question. If you're, so we're looking for the red to be minimum. Because the red line is the emissions. To me, it's kind of down here, like when you're stopped. Well, duh, if you're like not going, if you're 0 miles per hour, then you're not going to emit anything. Where does it spike? There's a spike. Oh, there's that because you're slowing down. I guess so. Because that's what you're doing, because you're going, and here's time. So in 20 seconds, is that reasonable? 20 seconds, you're going from 60 miles per hour to stopped. This is one right here. Oh, this is like stopping and going out on the highway. So the green line, did you get these words? I think I had engine speed, emissions, and acceptable limits. So that was hydrocarbons. This is carbon monoxide. Now, carbon monoxide is one of the ones that are deadly, right? So do the emissions kind of follow the emissions for carbon monoxide kind of follow the emissions for hydrocarbons? This next one, NOx, and X actually here in a minute we're going to say X could be 1 or 2, so it could be NO or NO2. Wow, that's crazy. So what happens at higher speeds to your NOx? It goes up. Yep. And then last but not least, CO2. Actually, I have a question. So I have a question coming up, and I'm open to suggestions, but one of your turn questions says, why is there not a green line here for CO2? Yeah, I think it's kind of wide open. There's no set, like, limit, yeah. Even though it's bad, you know, there's no set limit. Okay. So pictures, this one is describing, looks like I have some equations for you guys to write in. So this one is sulfur plus O2 going to form SO2. Is that balanced? Yep. So what's the name of this guy over here, SO2? Sulfur dioxide. Yep, sulfur dioxide. Ooh, here we go. And then we do this a lot in reactions. Can you see where what's produced here, the SO2 that's produced here, then becomes a reactant to our next thing? Okay, and this is SO2, SO2. What's this one, you think? It is O2. What's this one over here? SO3, yep. So in this case, we have 2 SO2 plus O2 goes to form, a reaction arrow, 2 SO3. So what's the name of this guy? SO3. Yep, sulfur trioxide. Is this balanced? Yep. And like the video said, although I think they had the wrong formula for it, one of the things with sulfur trioxide is it can actually react with water in the atmosphere to form, this is sulfuric acid, H2SO4 sulfuric acid. And one of the things we're going to talk about later is the problem with acid rain in our ecosystem. Then I say the good news, is that overall since '85 we have seen a reduction in this in SO2 in the United States. Okay. So the NOx I said was like NO or NO2. NO2 is a brown gas, and you're going to see a picture here in a minute. And what did we see with the NOx at high speeds for our cars? That's when we get the NOx's formed. And the way that works is the high temperatures in our cars, the high speeds in our cars gives us the high temperatures. So let's see, do you need to fill this one in? And this is really sad because in this room right now, what is the most abundant gas? Right, very good. So it's about 80-20, nitrogen and then oxygen. And check this out, you can actually get this poison, this nitrous oxide, this NO, it can actually form just from regular N2 and O2. Then we have a further reaction with NO. So here we have 2NO plus O2 goes to form 2NO2. So now here in this mix, not only do we have NO, but we have NO2. And that's what I said a minute ago, the NOx's are NO and NO2. Never mind. Your turn. Okay. So I think I'll give you a minute, but the first one is the NOx collectively represents oxides of nitrogen. If X equals 1 and X equals 2, write the formulas and give their names. You guys can do that. And then B, NO is the primary oxide that's formed first, and what's the source of this compound. And then C, we've already kind of answered. So, okay. Well, just tell me right, just answer together. What's the name of NO? I think we go nitrogen monoxide? Monoxide, nitrogen monoxide. Yeah, nitrogen monoxide. And then the other one you told me NO2 is nitrogen dioxide. And so on the previous slide, how did we get NO formed from N2 and O2? That's B. How did we get NO from just regular gases in the atmosphere? Providing heat, yep, at high temperatures. Exactly, high temperatures. Temperatures for B. And for C, I think we kind of, I would go with, there's the reason that there's, for the CO2, there's no green line, is there's no, CO2 in and of itself is not a toxin. So, all right, what else we got? Oh, another your turn. Okay, earlier, in chapter 2, we did a living downwind sort of thing, and we said you guys double-checked with regard to sulfur dioxide if this person was in peril based upon what she was exposed to. And now, actually, we're going to do kind of follow-up questions to that. So for both of these, you have to take these words, you get to take these words, and you get to make them into a chemical reaction. So for the first one, it says that silver sulfide, Ag2S, is heated in air to produce silver and sulfur dioxide. Okay. So your reactant is going to be Ag2S, and I'm thinking it's going to have to be O2 also. Does that make sense? Because what you're producing is an oxide. So I'll kind of get you started there. Ag2, and then you're going to have to balance this. Ag2S plus O2 goes to form silver. So silver is just simply Ag. And what's the formula for silver dioxide? Sulfur dioxide? SO2. So you need to balance that. And then the other one, copper sulfide, so is it reactant CuS, is heated in air. So I'm going to go ahead and put O2 because I can see it's going to produce an oxide to produce copper. So just regular old Cu. And then again, SO2. So go ahead and balance those. This one's balanced? We all agree with that? Oops, go back. What do you think? Works? Excellent. All right. NO2, other ways to make NO2 than just the high temperatures. Here's one where NO will combine with O3. What's O3? Ozone. And that's the thing you guys are going to test for tomorrow. So NO plus O3 goes to form NO2 and O2, just in the ground. And then I have a note here that actually the thing is that if you have NO and NO2, it can go back and forth between each other just with sunlight. The word here I have hidden is VOCs. If something is volatile, if a person is volatile or if a substance is volatile, what does that mean? Highly reactive, volatile, yeah. And in this case, what we kind of usually think is if something's volatile, it's reactive in the sense that it will evaporate pretty quickly. It's volatile, like rubbing alcohol is volatile. Okay? Things that you can smell, like perfumes, are volatile. So volatile, actually perfumes are an example of volatile organic carbon, and sometimes they're pollutant, depending on whose perfume it is. So volatile organic carbons emitted from vehicles will react with hydroxyl radicals, and it's OH is a hydroxyl group, and O dot means it's a radical. And it will also give us NO2. So you can kind of see a series of reactions here. The VOCs come from the exhaust of our car, okay? And I don't know, I had to look this up. That hydroxyl radical, that OH with a dot, there's not very much in this room, but there's enough to go ahead and be reactive. It reacts to form A, and A is just some sort of, represents some sort of, looks like I have the word hidden, reactive. Your A prime, and A double prime are just reactive organic carbons.
So what does the dot mean?
It means it's a radical. It's a free radical. Actually, and it has to do with its electrons.
And then what the A's?
The A's are just something generic. So sometimes it's just like a placeholder. Remember the other day I had R's on my kind of, it's just a generic, some sort of organic compound. So that forms A, and then that A reacts with more oxygen to form A prime. That's what we call that with a little tick mark. And then that A prime reacts with the NO to form A double prime, something else, just a generic reactive organic compound, and then ultimately end up with NO2. So in all of these, do you see that there's no A left? A is mutated from A to A prime to A double prime. So that the whole bottom line is you get NO2 from your volatile organic carbons. Oops. Was that it? No. Good. Not that I'm disappointed. Sorry. Okay, so here is the last part. So of today, part 5. So what is a catalyst? Do you ever? What's a catalyst? Speeds up the chemical process. It what? Speeds up the process. Speeds up the process. Yep. And one cool thing about catalysts is they are not consumed. It's like the burning bush where the bush was never consumed. So catalysts can be reused. So I don't even know what kind of car it was, but I know growing up that my brother had a catalytic converter. Do all cars have catalytic converters? They don't, do they? Do they? Oh my gosh. Shows you how much I know. So catalytic converters are our friend. They're actually a way to reduce pollutants. And the way they work is, so chemical catalyst is a substance that makes things go faster, but it's not consumed. So what they do under our cars is, remember how we talked about carbon monoxide is an unwanted thing during combustion? It's incomplete combustion. So it focuses on the carbon monoxide and it allows it to add more oxygen to make it into carbon dioxide. Now, granted, carbon dioxide is not good either, but carbon monoxide is a poison. So basically, it turns it into something that you have to be concerned with regard to global warming. So here I can see it converts carbon monoxide to carbon dioxide, CO2. And in the vein of a catalytic converter, newer cars are working on the nitrogen oxides. Remember, they're just released at high temperatures, okay? By actually capturing the nitrogen oxides and reducing them back to nitrogen oxide oxygen gases. Now, I just kind of want to look at what this would look like. Wow, that one just needs to be thrown away. So it'd be like a catalytic converter, but it would take that and reduce it into O2 gas and N2 gas. Much better, right? But I wanted the word reduce, kind of double check, make sure we're all on the same page. So what are the oxidation numbers of the nitrogen and the oxygen? They're in their uncombined elemental state. 0. Yep, these guys are 0. That's their oxidation number, oxidation state. Oxidation number. All right, so let's go over here to NO. And again, we haven't done enough of these for necessarily to just roll off. But what did I say oxygen usually is? Unless it's in like hydrogen peroxide. It's usually, remember? -2. Yep, its oxidation number is usually -2. And then if it's a -2, what's this nitrogen? It's a +2. Yep. That's okay. But it caught my eye when I was reading this because it says newer designs also limit the amount of nitrogen oxides by reducing them. And I think that this is one of the things. So which one's undergoing reduction? Nitrogen or oxygen? Yep, I agree. It's being reduced from a +2 to a 0. Yep. And so this guy's being oxidized. Anyway, it just caught my attention. Okay.
So, wait, is it saying that the newer design part, is that saying that newer design catalytic converters, they're not producing carbon dioxide, they're producing nitrogen and oxygen?
Oh, it is just the catalytic converter. So newer designs of catalytic converters, in addition to converting carbon monoxide to carbon dioxide, they're also trying to focus on this idea of reducing the NOx's back to something innocuous. So they're doing both. That's what I think. So ozone. Right? California, we decided might be a hot spot for ozone. Remember, ozone, you need sunlight and probably pollution. And they got both. But I like this series of slides. So this is in the morning. This is 5 a.m., 10 a.m., 1 p.m. Oh, start to see some O3 formation. The sun's out too. Sun's out, yeah. 3 p.m. Strat, right? 5 p.m. and then 11:40 p.m. So every day they kind of deal with this cycle of it going up and then coming down. All pollutants are weather related to a certain extent, I think. And this the source was this Air Now. Remember we looked at Air Now a while back. Oh, I see. So it looks like I have that the peak is around mid-afternoon and drops overnight. And then the other word I had here is sunlight needed to produce those volatile organic carbons needed to produce ozone from the VOCs and the nitrogen oxides. Okay? So O3 actually, there's not, if you go to a factory and look at what's coming out of the factory stack, you're not going to see ozone coming out of the factory stack. But it's not a direct pollutant, but it's an indirect pollutant. Okay, so it's secondary. So it looks like down here I have something that was hidden was NO2. Then over the arrow I have the word sunlight. When we write chemical reactions using chemical equations, a lot of times we'll put over the reaction arrow any special conditions. And in this case it's sunlight. It goes to form NO plus O2 balance. Oh yeah, but then the oxygen can react with O2 to form ozone. So this isn't normal O2. This is normal. Check those? Oh, okay. So tomorrow, like I said, we're going to be looking at ozone around here, and then we're going to take home something that's going to look at particulate matter. So let's take a quick look. I did have a video. I've got a video about green chemistry. So what do we mean by green chemistry? Chemists to the rescue, right? We talked about sustainability, and of course we kind of all generally have a sense for trying to save our environment. But for instance, plastics are usually made from fossil fuels. So if we can make plastic like Walmart sacks, plastic bags, from something other than fossil fuels, that would be a good thing. The next one is we're looking to create things that we use every day, like paints. Try to make it less, so our volatile organic compounds are not as likely to be associated with release of those. Cheaper and less wasteful ways to generally make things that we consume. limiting or eliminating the use of organic solvents. And then last but not least, this seems like a wild child. The last one is I guess there's an issue with regard to the element arsenic in our electronic devices. Try to remove that from the equation. Okay. Well,
Organic solvents is not going to be used to fracking or whatever.
Organic solvents for fracking. I've heard different things.
They dump some kind of acid down there, it's really good, and suck it out.
One of the things I heard about fracking was they just use water, but they use solvents.
Yeah, they use that.
Okay. Yeah, I thought it would have to be more intrusive than water. You know what side I was listening to, but I'm not really familiar with fracking, but it's bad. Don't do it. Yeah. Well, that's it for today, if that's okay with you. We get out early. Yay! Yes.
Do you happen to have like a study guide or anything?
One of my